session for 2023, and he's going to talk about TASEP's big brother, the totally asymmetric long jump exclusion process. Julian, the floor is yours. You can start when you want.
Yeah, thank you very much. Also, thank you to Clément who can't be here for inviting me and giving me the opportunity for this very nice seminar. So I will try to do everything from scratch, and I have more than enough time. So if you have any questions, just interrupt me, and I will try to clarify things immediately instead of waiting until the very end. Okay, so the big thing in this talk will be the TALJEP, or the totally asymmetric long jump exclusion process. And before we go into any more details, probably the most important question is why this weird name. It's just because all other possible acronyms would have been, I mean, just horrible, right? So it was the easiest thing to just put the stuff in the middle, and now it's TALJEP. It's easy to pronounce, and whenever I use the shortcut, you know what I mean with that. Okay, but let's start a bit easier, right? So some of you might already have seen the TASEP, which is the totally asymmetric simple exclusion process, right? So if you take one term after the other, so this part here just means that particles only go into this direction here. Okay, particle cannot go to the left. Then the simple means that the particles can only jump by one side at a time, so they cannot jump like from here to here. That would be forbidden, right? So this is that's not allowed. And finally, the exclusion part just says that particles will not be able to jump on top of each other. So this jump here would also be forbidden, right? And also jumping that direction forbidden. So all particles can do is jump one side to the right, and they do this at a constant rate 1. Right? For those who are familiar with the generator formulation of these models, that's just saying that we're looking at a Markov process, and this eta will always represent a configuration, which is nothing else as saying for every side on the integer line, either there is no particle or there's one particle, right? And then the generator simply becomes that for every side, I will look, is there a particle? If so, then I look to the right of it. If there's no particle, then I allow it to jump at rate 1. So the whole idea of this field of particle systems is then to try to understand what happens if we zoom out from this system and somehow scale space, perhaps accelerate time if necessary, and look at what are the macroscopic behaviors of the systems. And usually, or in everything, what we want to see is some sort of a deterministic macroscopic behavior. And then if we have this, then we can look at the fluctuations around this macroscopic deterministic behavior and so on. And so in the case of the TASEP, the main idea is to say, well, okay, let's look at the average density at some point, the average occupation time. And if I want to test that against a function, so if you think about weak formulation of PDEs, then this is what you usually would look at. And you want to know how this evolves over time. Then what you can do is to use the generator equation somehow, saying if you derive an expectation, it's the same as computing the expectation of the generator applied to the functional. And then either you can do the computations by yourself, or you just believe me that this is what comes out, right? So if you take the generator that I showed you before, and you compute this expression here, what you get is simply that. Okay, so when I talk about the gradient here, the discrete gradient, yeah, this thing is just g of x plus 1 over n minus g of x over n, and then divided by 1 over n. Right? And this is the reason why we see this weird factor in front of the derivative, and so which we will have to keep. And then for the rest, if we just naively say, well, this somehow looks like this, and this also looks like this, then we should be able to say, well, this should be the integral over the mean density at U times 1 minus the mean density at U, and then the gradient is this gradient here. The problem being that here, right, so here I have the expectation of a product, and now here I write the product of the expectations. This is usually not possible. So this is something which is like the crux of all the hydrodynamic limit proofs, is to show that this works. And this is what is usually called the replacement lemma. I will not have the time to go into the details of all the replacement lemmas we will do, or we will need throughout the talk. These are often very technical, but just that you know that there is actually an additional step to do here. And then somehow we have to take care of this factor here, right? And so the main idea is to say, well, what we do is we simply speed up time by a factor of n, right? And this takes care of this 1 over n, which is the same as saying, well, if you have this microscopic model and you want to see a macroscopic behavior, then what you need at least is that one particle moves a macroscopic distance, right? And for a particle, right, if you think of this from 0 to 1, and then you have this discretized lattice in between, and for a particle to move a macroscopic distance here, then it has to do order n steps in between. And so to really see something in the asymmetric models, what you usually have to do is to speed up time by a factor of n to actually see something. And then if you do that, then the equation that you had here, right, if you just read time derivative of this is equal to this integral here, which is the weak formulation of the Burgers equation. Right? Might miss a minus somewhere, but this is what you should expect. Okay, so here there's also technical details, right? For those who are familiar with Burgers equation, they know that this has many solutions, and to make these solutions unique, you have to add something that is called the entropy condition, entropy inequality. Again, if there's time left at the end and you have questions about it, then why not? But let's focus on other things for the moment. And so now this was all heuristic, right? And I have given no proof whatsoever. If you're interested in the details, there are multiple papers treating this. So there's a paper from Seppalainen in which he proves the hydrodynamic limits of the model, and then there are 2 important papers later on where they study Vardan and Coster study the large deviations. Right? So these are the large deviations of the model. And so somehow the TASEP, at least when you look at it on the whole line, Z is very well understood. And then so once this is done, the next question is, what do we do now? And there are mainly 2 things that you can do, right? The first thing is to say, well, now we've done these asymmetric dynamics on the whole Z, right? So perhaps instead of doing this, we can just put boundaries. So let's say here, right here, and then inside what we will call the bulk, the particles will do this exact same thing as before. So they're allowed to jump one side to the right. They're not allowed to jump on top of each other, and they're not allowed to jump to the left. But the thing is, once they arrive at the boundary, things change, right? They can't just continue. Instead, there will be additional interactions with the boundary so that particles can get in or can get out at given rates that I can prescribe. Right? So usually or often called alpha, beta, gamma, delta something. in some way or another. So this is the one idea that's possible to pursue, and this has actually been done in 2 recent papers by Lou. And the other thing that you might want to do, okay, so it works very nice. So let's stay on the whole of Z, no boundaries, but instead we allow the process to make long jumps, right? So we allow that they can be arbitrary long jumps, right? So this would still be prohibited because there's a particle, but except for the exclusion rule, any jump is allowed. And the only thing that we have to do is we have to weight these jumps in a way that makes sense, right? So the longer the jumps, the less likely they should be. But the way we will do this in detail, give me 2 slides. So this is the other thing that can be done. And this is a paper by Situraman from 2018, where they treat this model on the whole of C. Okay. So this is a picture which might be a bit better than my hand-drawn picture. So as you can see, it's the same thing. You're not allowed to go left. You're not allowed to jump on top of other particles, but you're allowed to make any arbitrary jump to the right. And this jump rate only depends on the distance I want to jump, not on so it's translation invariant. And then if I do that, and I can do the same thing as before, I can write it as a generator. So this time, as before, I will have configurations on the space of all possible particle configurations on Z. Now the only difference is that since I allow for all jumps, I have to sum over all possible departure sites and arrival sites. I still have the exclusion rule as before, and now I just modulate by jump rates P for well-chosen P that I will define in a second. Now in the paper from Sundar Situraman, and also what we will do later on, the jump rate will take this form here, and for the very simple reason that this is somewhat like a very natural thing to do to look at polynomially decaying jump rates. And the thing here is that if you choose this jump rate like this, then you actually have a phase transition, which happens exactly at gamma equal 1. So if gamma is larger than that, it means that jumps become very quickly very unlikely. And so on average means that the jumps are finite. On the other hand, if gamma is smaller than 1, then this thing has a finite mean, and so which means that we have quite often extremely long jumps, which might change the model drastically. And then there's this weird point at 1 where this thing is like the harmonic sum, and then we have some sort of logarithmic exclusion, which behaves a bit differently, right? Okay. And so what Situraman showed is that exactly as you would expect, there is also phase transition in the model itself, right? So whenever you have a finite average jump size, which is over here, there's no difference to the nearest neighbor model. The nearest neighbor. So TASEP. So in other words, we would expect to see the timescale to be hyperbolic. So n, I need n steps to see a macroscopic behavior emerge. And the limiting equation should be Berger's equation. And so this is everywhere here. Doesn't make a difference what gamma is as long as it's larger than 1. And even for this weird point here, also holds, with the only exception that here the time scale has to be adapted a bit. Time scale should be n over log n. This is not surprising. It's so somehow it behaves exactly the same. We just have to be a bit slower to take care of this logarithmic explosion in the jump rates. And then over here, where you have very large jumps, turns out that you will still see these non-local behavior acting on the limiting function. So you have some sort of, we call it fractional transport, right? Fractional transport. Some sort of Burger's equation, but with long-range interactions. And it also turns out that you have to go considerably slower than before. So the time scale is only n to the gamma. Right? So the smaller gamma, the larger the jumps get, the less you are allowed to speed up the process. So this thing here, I will actually define it later on. In our case, and yeah, it's I would say not a super nice formula, but it's not surprising, let's say. Okay, so this is all known. So this was all proven in that paper in 2018, right?
Julian,
and
sorry.
Yes.
Julian, I think there is a question from Cedric.
Sure.
Yes, thank you. No, just in the case where you have some infinite mean, in fact, you say that you have solution of the fractional Burger's equation, but in fact, it is not unique. At least we don't know if it is unique in the result of.
Yeah, that is exact. So that's something that I will come to later on, which is very problematic. That's totally true. So this thing here it's not known whether this thing here has a unique solution or whether we need more to characterize it. That is true.
Okay. You will discuss it. Okay.
Yeah, I will discuss it at a later point. Yeah. Thanks.
Okay, thanks.
Other questions? Okay, so as I said, this is all something that's known, right, since like now 5 years. And so what so there's still a hand raised, I think. But no? Okay. Well, okay, anyways. So what Patricia, Gonçalves and Lu Shu and I wanted to do now is to somehow, okay, now we've got these long jumps, and now we want to add the other thing. Can we add boundaries? What do we get when we add these boundaries? So somehow what you should think of is that inside the bulk, the dynamics are exactly the same as before. So you have long jumps, which are totally asymmetric, and you're not allowed to jump on top of other particles. So this is everything happens inside the bulk. And then additionally to that, you also have interactions with the boundaries. And here you can now have a lot of different parameters, which tell you how quickly a particle will jump into the bulk and jump out of the bulk on the left side or on the right side. And because you have these long-range interactions inside of the bulk, we decided to also put them on the reservoir, so that as before, you take the rate which is given by this p, and which only depends on the distance a particle has to travel. Right? So some of you might be familiar with the papers preceding, and then the PhD thesis by Stefano on the symmetric case, which I unfortunately don't have the time to discuss here, but it's closely related to this work. And then if you now say, well, okay, let's write this symbol for the generator inside of the bulk, so just describing how particles move when they're here. And then we write L minus and L plus for the generators describing the interaction with the left and with the right boundary. Then actually what you get is a Markov process, which now has configurations only here because we're only interested in the bulk. whether they are particles or not. And the generator is given by a combination of, well, the bulk for inside, what happens with the particles, plus the interactions with the boundary. And then here what we do is we modulate the strength of the reservoirs by an additional parameter, which means that if theta is positive, right, this quantity goes to infinity with n, so we have reservoirs that become ever stronger. And if theta is negative, then you have very weak reservoirs with vanishing effect in the limit. Right. Any questions for how the model is defined?
So I have a question, a quick question.
Yeah, go
So
on.
yeah, so you have a although your model is totally asymmetric to the right, at the boundaries you can go to the left in a sense, right?
So depends on what parameters you take. So you can also take completely asymmetric boundaries if you put, like, for example, the C out to be 0 and the C in to be 1.
Okay.
Right. So this is allowed. But we took the more general approach where we say, well, why not take general boundaries where you can get in and out and see what happens.
Okay.
Okay, so now this is more or less the big picture and what happens. There's a lot of information, but I'll walk you through it. So the first thing is, so on the x-axis here, from left to right, what you have is gamma increasing. So gamma increasing means the jumps become, on average, smaller and smaller. So these are the very large jumps. Oh, it's difficult to read it. I'm sorry. And here the smaller jumps, let's say. Both can have potentially very, very large jumps, but on average, right? These assertions are on average. And on the y-axis, you have the strength of the reservoir. So the larger you take theta to be, the stronger the reservoirs are. And the more negative theta is, in some sense, the weaker the reservoirs become. And now, just as a guideline for the rest of the talk, what we will do is we will take this diagram counterclockwise. We'll start in the red regime, and then we'll go through the different regimes. Okay. Now, some more details. So this thing here is the time scale that you will have to take in a different case, and you see that the time scale is actually varying continuously over the different regimes. So if you look at here the boundary, n to the gamma minus theta is the same thing as n to the gamma. Right? And here too, at that boundary here, both things are the same. And so as I said, right, so these are the very strong reservoirs. And so it's not surprising that here you get a reaction equation which says that somehow the bulk dynamics are completely irrelevant, and the only thing that counts is the interaction with the boundary. Whereas here you already see the 0-1 boundaries, which come from the fact that there's no interaction whatsoever, and so we don't really care about these interaction rates, C in, C out, whatever, because the reservoirs are so weak that they don't count. Okay. So let's start with this red regime here. It is so the result is quite simple. So actually, what you can get is that the TALJEP converges in the hydrodynamic limit to this unique weak solution.
Julian, sorry,
Yes.
there is another question from Cedric.
Sure.
Yes, sorry to interrupt you again, but so in all these regimes, do you have the uniqueness of the weak solution in some cases or not? Or everything is open?
Yeah, so what you have here, uniqueness is done here. Here, uniqueness is missing. It's the same problem as in the case from Seturaman, and I will come back to that. And this here is completely open yet. This is just a conjecture.
Okay.
Right, and so this here counts to the conjecture. This line also counts to the conjecture, and in this line we also miss uniqueness. Right, but I come back to these details in a second.
Okay, but in the case where gamma is bigger than 1, so you establish some entropic inequalities like in Rezakanlu, or? No, I mean to have some uniqueness. You say you have uniqueness, so it means that you have to establish some.
Exactly. So you have to somehow prove the complete Berger equation with the entropy inequality.
Okay. Thanks.
Also, in the red case, it's actually, I think, the easiest case, because what is very nice is for this equation here, you have the explicit solution and you can prove uniqueness. And so the convergence of the hydrodynamic limit is rather straightforward. There is one detail which is important, so let's come back here. So here at this point here, the reservoir dynamics become problematic at the boundary. So they explode so fast that you actually have to be careful about what your solution can or cannot be. And so actually what you have here is that in this case, you can look at all possible boundary interactions, whereas here you're not allowed to look at the totally asymmetric boundary. So this is just to tie in with what we had before. So this is, here everything is allowed, there's no problem, everything goes through. Whereas here, because of the limitations of the entropy method, you cannot take the completely totally asymmetric boundaries. Right? So you have to allow to get particles out on the left and to get particles in on the right. And so for the rest of these V0 and V1, they can be explicitly given, but it's rather technical, so I will not write them down here. And these are the usual boundaries that you would expect in this case, right? These are the equilibrium boundaries. Now, the more interesting regime is everything that comes beneath that. So we're looking at the orange regime and at the line, right? So the orange regime is theta smaller than 0, and the line was the part where this is equal to 0. And in all these cases, we see the non-locality survive to the limit and not being destroyed by the strong reservoirs. And so as mentioned before, you do not have the uniqueness of this equation. And so the only thing that you can show that the sequence is tight and that all limit points are solutions to this equation. And so the equation itself, so this is the fraction transport part that I will define in a second. And then if theta is smaller than 0, this term just goes away. But on the line, you also have this you have this reaction term from before, right? And then what you see at the boundary is that you actually have Dirichlet boundaries. And these rho minus and rho plus will be given in a second. Only the more interesting thing is that actually in the cases where theta is smaller than 0, you actually have 0,1 boundaries, right? So you start here and then you have somehow to go up, which I will discuss from a different point of view later on.
So this is what you mean by 0,1 boundary?
Yes, so when I say 0,1 boundary, I mean that it's a Dirichlet boundary with 0 to the left and 1 on the right.
Okay, thanks.
Okay, so now it becomes a bit more technical. So whereas in the Berger's case, you're looking at something like this, if I'm not mistaken, rho 1 minus rho. where this was the flux that you would see at one point. Well, here's the same thing. Here, what you should think is that the variation in time is just the flux that you see. So the number of particles coming into the side u is just all the particles between 0 and u that can possibly jump to u. So there has to be a particle at v and no particle at u, and then the jump rate, and then minus the particles that jump out. So they can jump to the right of u, and there has to be a particle at u and no particle at the arrival side times the jump rate. Now, you will see that this is not super well defined, right? So this thing explodes very quickly when you get close to u. But in the weak formulation of the PDE, this is actually well defined and not a problem. So we only need L infinity regularity for this to work, which is given anyways. And for the boundary points, this looks very complicated. So I will go back to the actual definition of the boundaries, which is also very different from what one might expect, right? So the boundaries are not defined as classical Dirichlet boundaries. They are defined through this limit, which is taken. This limit is taken in L2 of time. And what it says is also a sort of flux equality. So it says that the flux that goes away from 0 into the rest has to be equal to the flux that comes from the interaction with the reservoirs. And if you, for a second, were to assume that rho is continuous, at least at the boundaries, then you can explicitly compute those integrals, and they're exactly the same as saying this, which is again just some sort of flux equality, and which you can solve because it's just quadratic in rho of 0. And it will turn out that there's only one solution that is admissible in the sense of a density, and this is the one that I wrote down before. And so for the right hand side, you can do the same. But, and that's the important part, it's not a classical Dirichlet boundary.
Another question.
Yes.
Yeah, so if I understand well, it means that you don't know that rho t is living in some Sobolev space or something like that.
Nothing.
You don't have some energy estimate?
No. So the classical things that you would see in the symmetric case, they all don't work. And so it's very annoying because you would actually expect, so you would like to compare it to Berger's equation, but Berger's equation is very ill defined. So you see shocks appearing in finite time. But on the same time, you would think, well, these long-range behaviors they should help smooth out stuff, which means that you would expect the solution to be smoother as the Berger's equation, but it's not clear how smooth. At the moment, we're trying to understand whether we can show at least the continuity at the boundary, but even that is open at the moment. And also in the paper from 2018, there's no regularity result on
yeah. Mm-hmm. Okay. Thanks.
Yeah. So these are like what we just did was so this is fine, right? This is rather well understood, I would say, with this slight restriction here. Not totally asymmetric at the boundary. But I mean, so this is, I mean, that is a common restriction. That is, yeah. I mean, it's still sad, but it's okay, I would say. And here it's just annoying that we cannot get uniqueness of the equation and regularity, but this is something I come back to later. And now to go on, actually, we will change completely the method. So what?
Sorry, can I just comment a little bit?
Mm-hmm. Yeah, sure.
Yeah, I just wanted to comment a little bit on because I will say that in this case you should be able to get some sort of energy estimate, but in a Sobolev space which does not imply continuity. That will be the natural thing to get.
Yeah, I guess you're thinking about these gamma half Sobolev spaces, this fractional Sobolev with less than one, right?
Yeah, exactly.
We would very much like to get something like this.
Sorry, but I didn't understand. What is this this non-Sobolev energy estimate? What it is? It is
I mean, there should be an energy, okay, but it's a non-local energy, and so there is some functional space. But this the thing is that a function belonging to this functional space does not imply continuity.
Yes.
so. But what you can do with this kind of estimate?
No,
So
well,
you do that.
yeah, you cannot do a lot. I mean, you can do some things, but not too much. I mean,
so as far as I'm concerned, I mean these estimates are somewhat, at least in the symmetric case, important to get uniqueness of the corresponding equation, right? So if you restrict your solution to this more regular Sobolev space, then you can get uniqueness.
Okay.
But I mean, at least we're not able until now to get these energy estimates in the asymmetric case. But I mean, it's not unthinkable, and we think that we should be able to get them, but until now we have not been able to.
Okay, thank you.
Yeah. Yes, that's fine. I have 5 minutes left. Okay. Good. I would just very quickly talk about these regimes, right? So everything that I talked before was rather classical. So you try to understand the entropy method and try to show these results. But actually, there's a very simple method for these cases here, where you look at the very weak boundaries. And the idea is extremely simple. So you have your system, and inside the bulk, everything is allowed, right? So there's no restriction on, or mostly no restriction on, what dynamics you can have. The only important thing is that your dynamics with the reservoirs are weak. So in the case that we looked at in this talk is that we have this n to the theta, and theta being negative, so this goes to 0. And that means that the interaction with the reservoirs are extremely rare, right? They become rarer and rarer when n goes to infinity. And even more importantly, to have many interactions, that means that it's super rare. And if you actually want to have enough interactions to make a macroscopic difference, so this means O of n interactions, right? Order n interactions, then this becomes impossible. And more precisely, what you can show is that you look at the very large class of processes. For the experts, I'm talking about the misanthrope processes, so the one that you can couple in a nice way. And these include both the TASEP and the TALJEP. Then you can actually compare the boundary-driven version with very weak reservoirs to the version where you don't have any interaction with the boundary, right? So this is not very surprising, but you can actually show that they're exponentially equivalent. And that is very nice because that means that you can just, if you know the hydrodynamics or the large deviation for one of them, then you immediately get it for the other one too. And so for many models, this might not immediately be helpful, but for asymmetric models, this is extremely useful. Because if you now compare dynamics here on a bounded interval where there's no interaction with the boundary, and the same model, but on the whole of Z, but with the very particular initial configuration that you have no particles to the left and only particles to the right, then what happens is that these two things are the exact same thing, right? In the asymmetric exclusion processes, that's important here, because particles are not allowed to jump outside to the right, and there's no particles coming in from the left. And because it's asymmetric, the other way around can't happen anyways. And so as soon as you know the hydrodynamic limits on the whole of Z, you automatically get it for the one with the closed boundary, so no interaction, and then because of exponential equivalence, you immediately get it also for the weak boundaries. And that means that because C2-Raman has these results, so here fractional transport and then here Burgers equation, well, we get the same thing, right? So without computing anything, the same thing is true for the TALJEP. Same thing true for TALJEP as soon as we have weak boundaries.
Sorry, what is a TALJEP exactly?
That's just the name that we gave the totally asymmetric long jump exclusion process. So the thing that...
But you have to choose gamma.
Gamma can be anything. Then we have the same behavior as in C2-Raman's paper. So for gamma smaller than 1, fractional transport, and for gamma larger than 1, including 1, Burgers equation.
Okay.
Right. So the only thing that has to be noted in addition is that the boundaries are very weak. And so, I mean, the problem is the same because we just transport and translate the results from C2-Raman. We don't have uniqueness here. So that means that we do not have convergence, but only identification of the limit points. And here, because there are these restrictions on the initial condition in his paper, we have also restrictions on the initial condition. So we only can have as good a result as it already exists in the case of on the whole line. Right?
Sorry.
Yes.
What do you mean by exponentially equivalent?
Exponentially equivalent in the sense of large deviations. So it means that the J1 difference, the norm, the J1 norm between the two processes, being larger than some epsilon, goes to 0 super exponentially fast.
Okay, thank you.
Is that helpful?
Yeah, thanks.
Okay, so actually, I mean, in this case, there's no large deviations known for the TALJEP on the whole line. But if there were, you could also immediately translate fluctuations and large deviations over to the one with weak boundaries. Okay, so I will use the last 5 minutes that I have to speak about the problematic regime, which is here, right? So some open questions. This will include the things that we already mentioned, so regularity and uniqueness. This will also include these problems with the initial condition or initial condition. and also what we want to do here, right? So to do so, I'm very, very sorry, but I will have to talk about Young measures. I know this is not a topic which is with which many are familiar, and I only have 5 minutes, so I can't go deep into it. But if you found the stuff interesting that I said, I think I can invite you to learn more about Young measures. They're very nice objects. But for the rest of this talk, the only thing that you need to know is that Young measures are somewhat generalized functions. And the good thing about Young measures is that convergence becomes very easy. Good. And the reason why we are interested in Young measures in the asymmetric regime is the following problem. When you only have a hyperbolic time scale, which is n, then the usual methods that you have are only able to show the replacement lemmas for boxes of finite size. And that's not good, because when you have here x and you want to see a macroscopic behavior, then you would hope that the behavior in very small but macroscopic boxes is somewhat similar. So you're interested in boxes which have size epsilon n for epsilon small, right? But still of order n. And the only thing that we are allowed to do at this time scale somehow is to exchange eta x by the average over over large microscopic boxes, which are too small to actually pass through the hydrodynamic limit. And so it's not enough to get the conversion in the space of functions. But it is enough to get the convergence in the space of Young measures, because convergence is super easy for Young measures, which is very nice. And then the problem only becomes, okay, now you have a Young measure limit, but you only wanted to have Burger's equation as a limit, so you wanted to have a function as a limit. So now you have to prove that somehow the limit, which is only a Young measure, is actually a function and is solution of Burger's equation. And as far as I am aware, there are mostly two strategies to do this. There's on one hand, the Panner's uniqueness argument, which was used by Sunda, and compensated compactness, which was used by Liu in his 2 recent papers on the TASEP. And for the Panner, which is very nice, is that you actually don't care if it's a function or a Young measure, because you get that automatically at the end. But, and this is where it comes in, the very strong assumptions on the initial conditions, right? So this is where the problem comes from, is that to use the Panner's uniqueness argument, you need a good convergence at time 0. And the second thing is, but which is not surprising, you need to show some sort of microscopic entropy inequality to get uniqueness of the limiting equation. Now, for compensated compactness, which is extremely nice, is that you have no assumption on the initial condition, which is necessary. But, and this might be even worse, is what you need vanishing viscosity. What does that mean? That means that you have to allow particles to also jump to the left. So you're not allowed to be totally asymmetric. The symmetric part is allowed to vanish in the limit, so it is allowed to go to 0, but it has to be there in the pre-limit. And this is, I think, quite annoying, because it changes the model, which is not nice. But until now, it's not known whether these models, I mean, they should behave in the same way, but it has not been proven. And so until now, the compensated compactness method really needs this vanishing viscosity part, both to show the microscopic inequality and to show that the Young measure is actually a function. But the thing is that actually when you go through the different proofs and you want to do this is at least the proof that is from in Sunda's paper relies heavily on the fact that we have product stationary measures, right? And this is not the case anymore when you're boundary driven. And so what we decided to do when we want to prove this last regime, this green regime and the lines that go with it, is actually to focus on the compensated compactness method and try to see how far we can get, and perhaps we can even get this vanishing viscosity part down either to 0 or to vanishing even quicker. Yeah, so as I said, that's work in progress, trying to prove the last regime of the 4 regimes, which is using a completely different method than for the other regimes. And there are a lot of open questions. So as we've seen before, we need to, or we want to have regularity for the fractional transport equation, and we also want to have uniqueness for the fractional transport equation. What we think is reachable is something like continuity at the boundaries, at least in the case of weak reservoirs. This is something that we think one should be able to get. If continuity everywhere, I don't know, numerical simulations suggest that the solution should be continuous, but well, that's not a proof. Then the second thing is this problem with the initial conditions. So in Sunder's paper, and so by extension also in our case, with weak boundaries, you have to assume that the initial condition is continuous. So the profile is continuous, and the initial condition is product, which is very restrictive. And so it would be nice to actually have more general initial conditions. But then you can probably not use the fairness argument anymore, and then it's not clear how you show convergence on the whole of Z. And I think one of the holy grails would actually to improve the method of compensated compactness, so that you don't need this viscosity part anymore. And then I think it's the much more powerful method in the case of asymmetric exclusion processes. Thank you very much. If you have any questions, just go ahead.
Thank you very much, Julian. If you want, you can unmute yourself and we can thank you properly. So there is a question from Lou and then Cedric.
Sorry? Can you hear me?
Please go ahead. Yeah.
So you said the Sunda need a very restrictive initial condition. Then can you still start from the profile that you have 0 on left, 1 on right?
Very good question. No, you need then that your initial profile is continuous on Z, which means that on the box you have to already go to 0 on the left and go to 1 on the right when you start, which is one of the annoying features of this restriction.
Okay.
Cedric, I think also has a question.
Yes, thank you. So it means that in the case of a fractional transport equation, you expect to have some regularity of the solution. You don't have shocks.
So I mean, okay, so there are a few things there. It's the problem is that if you start with this solution, with this initial condition, then you can't expect to get any regularity because it's stationary, nothing should move.
Mm-hmm.
But as soon as there is some movement allowed, then I think so at least from what I've seen from numerical simulation is that the solution becomes smooth very quickly, instantaneously. So what I did, for example, is to start, well, let's start with this initial condition, right? And then it became extremely smooth right away.
So it is very different from the nearest neighbor case.
Yes.
Okay. And some other question I had, I think it was in the beginning of your talk, you were mentioning some results for the large deviations. And there are some, I think, some QL. So Q is maybe Questel, and the L is what?
The T here.
Oh, T. Yes.
I have it at the very end. I'm not, so it's Questel and Liching Tsai.
And what is the result? What it is?
So in the Varadan paper, what you have is the upper bound for the large deviations for the TASEP, and they show the full.
Which paper are you mentioning? It is the thesis of Jensen, the thesis of Jensen Varadan, you mean?
So there's another one from Jensen Varadan. I don't remember if it was before or after this one, but there's also a paper from Baradan alone from 2004, where
But
he
what is in statistical? Yes, but in this case there is a okay. As understood, there is a lower bounds and upper bounds in this paper of Varadan.
but
But
the
there are some
not
discussions
complete.
about it. But,
So it's this thing here, the large deviations are not yet complete. I think there's a gap between the upper bound and the lower bound.
okay,
So
and in the QT, QL, QT, I don't remember.
yeah.
There is a complete proof of the large deviations principle.
Yeah, as far as I understood it, yes. I have not gone through the details yet.
Okay, okay.
But yeah,
Thanks.
so as far as I understood it, it has a complete large deviations, but formulated in the language of the interface model.
Yeah, okay. Okay. Thanks.
Let's see if there are more questions. So I have a question. If so, what is the physical motivation of having this long range interaction both in the bulk and this reservoir that can act far away?
I will not be able to answer.
Okay.
At some point I asked myself the same question and I found some things, but since then I forgot. I think for the very specific model that we are looking at, it's more the question of how far you can push the methods. It's try to, okay, can we get also to long range? Can we put boundaries and stuff? At least our model is not immediately based on any nice physical implication.
Okay, thanks. Let's see. I think.
May I ask a question?
Milton, yes, please.
Yeah, so maybe it's not completely related to this, but I'm just curious. It's so let's say that you put just one boundary. Okay, so you have semi-infinite line, and well, then if you do the TASEP with one boundary, you expect maybe to converge to a completely full profile. So there should be some conditions for that, and I don't know if this is and if one can, for example, study the speed of convergence or things like this through this methodology.
That sounds interesting. I've never thought about having just one boundary. So you're thinking about having a boundary on the left-hand side with particles coming in, and then the question whether it fills up on the right.
Yeah.
That's very interesting thoughts. I have no idea, but that's I will keep that in mind.
Okay. Thank you.
Okay, let's see. I don't think we have more questions. Okay, thank you very much, Julian. And thank you everyone for attending. I think we will go back to the series of seminar in the second week of January, so after the winter break. Bye-bye.
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 Bye. Thanks again for
Bye, Julian.
the opportunity.